In this presentation, I'll be explaining alternating circuit, AC circuit with load RL, resistance and inductance only. Then AC circuit with R and C, resistance and capacitance. And then finally, I'll be explaining AC circuit with resistance, inductance and capacitance, RLC. Coming to the contents of this presentation, first I'll be explaining AC series circuit with R and L load. This RL load and AC series RL load circuit, and AC series circuit with resistance and capacitance. And third, I'll be explaining AC RLC series circuit. That is, AC input is given through RL and C. They are connected in series. Therefore, I'll be explaining one by one. Let us see first an RL circuit. In an RL circuit, and what do you mean by the impedance of a circuit? Therefore, let us see the concept of the impedance in an RL circuit. Therefore, this is a RL circuit in which the voltage source is there, resistance R is there, inductance L is there, and this is a current flowing through this circuit. And if you see the corresponding instantaneous voltage and current, this is the instantaneous voltage. And of course, we'll see that one, the current is lagging the voltage by a certain angle phi, which will be in between 0 and 90 degree. For example, if the purely resistive circuit, you know that current and voltage are in phase, for phase angle equal to 0. But for a pure inductive circuit, the phase angle equal to 90. The current is lagging the voltage by 90 degree. For a RL circuit, the phase angle between the voltage and current will be in between that one. Therefore, it will be between 0 degree and 90 degree. Now, let us see that is equal to phi angle. The current is lagging the voltage by an angle phi degree. Therefore, this is the voltage and this is the current, instantaneous value of the current. And if you take the product of that one, we'll be getting the power. And the product here, if voltage and current both are positive, we'll be getting positive power. And if both are negative also, you'll be getting a positive power. If one is positive and another negative, you'll be getting a negative power. Therefore, the area under this power curve represents the energy. Therefore, here the current is lagging the voltage by an angle phi. Now, if you consider this again, the vector wise here, this is the current vector, that's current flowing through the resistor. As you know that one, the current and voltage, they are in phase for a pure resistive circuit. Or resistive circuit, if you say that one, voltage across the resistor is in phase to the current. That is why VR is, we are drawing in phase to the current. Of course, the voltage across this one, inductor, is of course here leading the current by 90 degree, or can say the current is lagging by 90 degree. Therefore, this is the voltage vector, that's voltage across the inductor, which is leading the voltage across the resistor by 90 degree. Therefore, the total voltage is the vectorial sum of the voltage across the resistor and the voltage across the inductor. You are adding these two things. Therefore, you are adding, you will be getting, it is a rectangle triangle. We can get what is the net voltage, capital V. So V equal to, of course, it is equal to the square root of VR square plus VL square, or the voltage across the inductor square plus voltage across the resistor square. That is the net voltage coming here. Therefore, in an RL circuit, current lags the voltage by an angle phi degree. Here, current is lagging. The instantaneous power can be calculated by multiplying the instantaneous voltage and instantaneous current. And if you see here, we have seen the net voltage V square equal to VR square plus VL square. Substituting here, V equal to, it is equal to the current into next. This is the impedance. Capital Z is the impedance. That is, looking from this one, what is the, of course, the resistance offered. That we call it as, it's an AC circuit, it's called impedance Z. Therefore, I into Z is the voltage V, that whole square, equal to, again, current I into R whole square plus I into XL whole square, or inductive reactance XL, that whole square. Now, reducing this one, we can get I will be cancelling here. Z squared equal to R square plus XL square, or we can get Z equal to square root of R square plus XL square. This is the impedance of RL circuit, root of R square plus XL square. That is the magnitude of the impedance, where XL is called the inductive reactance, which is equal to omega into L, or 2 pi f into L. The unit is equal to ohms. Therefore, reducing the equation here, we will be getting Z equal to root of R square plus XL square. And in rectangular coordinates, for an RL circuit, we represent it as R plus JXL. R plus JXL. Or for example, this is the impedance triangle of an RL circuit. That this is a resistance and this is the inductive reactance XL, and the vectorial sum is called the impedance. This angle is equal to the power factor angle phi. Therefore, here this Z can be represented as R plus, because this is a 90 degree, say 90 degree it is there, that J represents a 90 degree shift in the anti-clockwise direction. Therefore, this this vector Z can be represented as R plus JXL for an inductive circuit. Or in polar coordinates, the same thing can be represented as Z angle phi, where the Z equal to, it is actually the magnitude of Z into angle phi, but the magnitude of Z is equal to root of R square plus XL square, root of R square plus XL square. That is, that phi equal to, of course, this phi equal to tan phi equal to XL by R, or phi equal to tan inverse XL by R. Therefore, there's another way of representing this in a RL circuit. The polar coordinates we represented as impedance as Z, modulus of Z angle phi, and in rectangular coordinate it will be represented as R plus JXL. Therefore, that is the impedance definition of an RL circuit. And power factor is given by, of course, this is a power factor angle. Power factor, one way of representing power factor, cos phi equal to R by Z. Where, cos phi equal to R by Z, or tan phi can be represented as XL by R, or phi can be represented as tan inverse XL by R. Where this is called the impedance triangle. And in all this case, R, XL, and Z, the unit of all will be in ohms. Coming to the power in an RL circuit, then again same RL circuit. This is instantaneous voltage and instantaneous current. Product is equal to the instantaneous power. Instantaneous power can be calculated by Vm sin omega t into Im sin omega t minus phi, because current vector equation is equal to Im sin omega t minus phi. Phase angle shift is there. So if you take the product of that one, we'll get power equal to Vm Im sin omega t into sin omega t minus phi, or Vm Im into, if you take, it is equal to half of cos omega t minus phi, or minus cos omega t into cos omega t plus phi, or that can be reduced as Vm Im divided by 2 into cos phi minus Vm Im divided by 2 into cos 2 omega t minus phi. Therefore, if you take the average value of this, average real power is given by, it is equal to Vm Im divided by 2 cos. This is called the real power average value is equal to Vm Im divided by 2 into cos phi. Or it is equal to, for an AC circuit, the power equation is that Vm by root 2 into Im by root 2 into cos phi, or V into I into cos phi, where V is the RMS value of the voltage and I is the RMS value of the current. Cos phi is called the power factor, where phi is the phase angle between the voltage and current, that is phi. Therefore, this is the active power, we call it as active power, Vm Im divided by 2 into cos phi. And the oscillating component of power, this is called the oscillating component of the power, which is with respect to time, it is oscillating. And the oscillating component of power is equal to this one. Therefore, the active power in a AC circuit is given by Vm divided by root 2 into Im divided by root 2 into cos phi, or Vi into cos phi. Again, continuing the power in an RL circuit, same circuit here. Active power, as you know, it is equal to Vrms into Irms into cos phi, or reactive power is given by Vrms into Irms into sin phi. Therefore, where Vrms is the RMS value of the voltage, which is equal to Vm by root 2, Irms equal to RMS value of the current, which is equal to Im divided by root 2. Therefore, this is called the real power, and this is called the active power, or real power, or true power, and this is called the reactive power, P and Q. Therefore, here, as we have seen that phase phi is the phase angle between the voltage and current, or we can say that one phase angle between the voltage and current, or in RL circuit, phase angle will be, as I already told you, phase angle between 0 and 90 degree. 0 and 90 degree. Because for R, it is phase angle equal to 0, because both are in phase. For inductor, pure inductive circuit, it is equal to 90. For an RL circuit, the phase angle phi will become in between 0 and 90. For example, 30 degree, we have calculated active power, which is equal to Vrms Irms into cos 30, which is equal to Vrms Irms into 0.866. And reactive power also can be calculated, and 0.5 Vrms into Irms. As a complex quantity, we can get the real power can be S equal to, or the real power I am calculating as P, and reactive power is represented as Q, or the apparent power S equal to P plus JQ, or the apparent power is equal to this. It's called the power triangle. This is the active power, this is the reactive power, this is the apparent power, and we can say that this S equal to P plus JQ, where S equal to square root of, this is a complex quantity, and the magnitude of this one, we know that it is equal to square root of P square plus Q square, or the phase angle phi equal to tan inverse Q by P. Tan inverse Q by P, it is the phase angle. Therefore, this is the Another way of definition of the power factor is also one more is the active power divided by the apparent power. Cos phi equal to active power divided by the apparent power. Therefore, this is the power in an RL circuit. Now let us see the concept of impedance in an RC circuit. Previously we have seen RL circuit. Here in RC circuit, same thing. Instead of inductor, there's a capacitor. Resistance is capacitor. As you know that one, this is a voltage. And in an inductor, if you see that one, the voltage across the capacitor, you see that one, since the current vector in the series circuit, can say that this is a current vector, and to that one, the voltage, of course the voltage across the resistor that is in phase to the current vector, but voltage across the capacitor is lagging that one by 90 degree. Therefore, the net voltage can be calculated. The vectorial addition of the voltage across the resistance and voltage across the capacitance, vectorial adding, we will be getting an angle. This is equal to the net voltage that is here. For that voltage is making an angle with respect to the current by an angle phi. That is called the power factor angle. Of course, here the current is leading this voltage. The current that is flowing here is leading this voltage by an angle phi. Therefore, this is the voltage triangle, same as this one, voltage triangle, and this is will be, this is called impedance triangle. In impedance, if you take the impedance case, as we have seen in the case of inductor, here resistance is this one, and this is called the capacitive reactance XC, and this is the total impedance Z. We'll see that in the impedance equation in the next slide. Therefore, the current is leading the voltage by an angle 5 degrees, so the power factor is leading. In a capacitive circuit, the power factor is leading, or current is leading the voltage by a certain angle. Therefore, this is the instantaneous voltage, and we can see the instantaneous current. Take the product of that one will give the instantaneous power. Positive power, that is power consumed. Here, this is actually negative power, means that it is the power is returning back to the source. For that negative power, here actual power being consumed, and you can calculate what is the average power consumed. And this is the instantaneous voltage, current, and power. And is the voltage across the voltage resistor and capacitor. Now continuing the concept of impedance in an RC circuit, as we have seen already in the inductive circuit, here it is resistance and capacitance here. Therefore, same as this one, you can you can say that the voltage across input voltage V equal to VR square plus VC square. The voltage is the sum of the VR square plus VC square is the total voltage. Or substituting that one here, vectorial sum of these two voltages is equal to total voltage. Therefore, I Z square, where Z is called the impedance. Substituting this equation, IR square plus IXC square. Again, where XC is called this XC is called the capacitive reactance. XC equal to 1 by omega C, which is equal to 1 by 2 pi FC. Therefore, the reducing this equation, we can get it as I squared gets cancelled, or Z squared equal to R square plus XC square, or Z equal to root of R square plus XC square. Again, the impedance equation in this case also, RC is equal to square root of magnitude of the impedance equal to R square, square root of R square plus XC square. In rectangular coordinate, it will be represented as Z as represented as R minus JXC. See the impedance triangle is this one. This is the resistance, and this is the capacitive reactance, and this is the total impedance. We can see that one. Here, see, this is XC is in this direction. Previously, XL it was in the upward. Here, there is why this in minus J is there. Here, minus J is there. It is actually a rotation in the clockwise direction. That is why minus J comes. If the rotation of the vector in anti-clockwise direction, it will become plus J. Therefore, here, Z is the minus JXC, that is the total impedance Z. Therefore, this is the representation of the impedance in rectangular coordinates. Z equal to R minus JXC. And in polar coordinate, Z equal to magnitude of Z into phase angle phi, where magnitude of Z equal to square root of R square plus XC square, and phase angle equal to tan inverse minus XC divided by R. Minus XC by that's called the phase angle. So this is a polar coordinate representation of the impedance of a RC circuit. Of course, power factor is given by the ratio of the resistance divided by impedance. Of this power factor equal to R by Z. Power factor equal to R by Z, or phi equal to cos inverse R by Z. Another way of defining the power factor angle, tan phi equal to, if you say that tan phi equal to, it is equal to XC divided by R. XC divided by, of course, minus sign is there because here minus XC by R, or phi equal to tan inverse minus XC by R. That in this case, current is leading the voltage, or can say that voltage is lagging the current. That is why that negative sign comes here. Therefore, this is the impedance in an RC circuit. Therefore, this is called the impedance triangle, and this is a voltage triangle, that is the total voltage, and this is the voltage across the resistor, and this is the voltage across the capacitor. Vectorial sum is the total voltage that is at the input side. Therefore, this angle is both are same, phi and phi. This is a power factor angle. Again, the power in an RC circuit, in order to calculate, we have to calculate the active power is given by V equal to Vrms into Irms into cos phi. Same equation as we already seen. Reactive power equal to Vrms into Irms into sin phi. Vrms equal RMS value of the voltage, Irms RMS value of the current. Phi is the phase angle between voltage and current. But in this case, phi is equal to again the angle is between 0 and 90, but it's called leading current. That's why power factor equal to, we call it as leading the power factor. Again, for example, it is equal to point for a 30 degree, 0.86 leading here. You can calculate what is the active power and what is the reactive power. Of course, the apparent power is equal to the square root of real power or active power square plus reactive power square. That's called apparent power. Another way definition of the power factor, as we have seen, it is equal to the active power divided by the apparent power. Therefore, this is the active power and this is the reactive power. This is the apparent power. Again, one more, based on the power, it can be expressed as P by S. That is a power factor cos phi can be represented as P by S for active power divided by apparent power. Now, continuing the concept of the impedance in an RLC circuit, here resistance, inductance, and capacitance both are all are connected in series to a voltage source. Of course, you can see that one. This is a voltage source. Here, this is a voltage signal that is coming. As you know that one, if you see that, of course, this is a voltage signal, or of course, this is the voltage, or this is as shown as a current signal. This is a current signal. Now, if you see the voltage across the resistance, that voltage is in phase to this current. Now, if you see the voltage across the inductor, you can say that one, the voltage across the inductor is, leading the current by 90 degree. This voltage drop is leading this one by 90 degree. Now, for the voltage across the capacitor, we can say that one voltage is lagging the current, or we can say that current is leading also. The current voltage across this one is lagging this one by 90 degree. This vector is shown here. This is the current vector, and this is the voltage across the capacitor, and this is the voltage across the, of course, this is the voltage across the inductor, and voltage across the resistance is here. This is the VR, and this is the VC, and this is the VL, voltage across the inductor. That is, as a waveform, it is shown here. Now, coming to the vectorially representing here, of course, this is a current vector, and to the voltage across the resistor is, the voltage across the resistor will be in phase to the current. As you know that one, always the voltage across the inductor is in phase to the current. That is why the current voltage vector is in phase to the current vector. Another one is that voltage across the inductor is leading the current by 90 degree, or you can say current is lagging by 90 degree. That is why this is the voltage across the inductor VL, and this is again the voltage across the capacitance, which is lagging this voltage by 90 degree. Therefore, if you add these two things vectorially, if you add, the net voltage is equal to VL minus VC. Here VL is more than VC, therefore the net voltage will become VL minus VC, and that is added with VR, you will be getting the net voltage. Here the VL is this one, VC is this one. This difference is equal to VL minus VC, and that VL minus VC is added with the VR, then we will be getting the total voltage that is coming here. So this voltage is equal to the vectorial sum of the voltage across resistor, inductor, and capacitor, that is this one. Now, this is the case when XL is more than XC. The inductive reactance is more than capacitive reactance. This happens because in that case, VL will be more than VC. But another case, when XC is more than XL, therefore VC will be more than VL. See this one? Here VC will be more than VL, so that this is the net voltage that is between inductor and capacitor. That is vectorially added with the voltage across the resistor. Therefore, this is the net voltage. The net voltage. Of course, in this case, current is leading the voltage by an angle phi. But in this case, we can say that current is lagging the voltage by an angle phi. Therefore, this is after connecting, this is an inductive circuit, and this is a capacitive circuit, because in this case, inductive reactance is more than capacitive reactance, but here capacitive reactance is more than inductive reactance. Therefore, the phasor diagram corresponding to XL is more than XC, not phasor as a voltage diagram as such, voltage vector diagram. Here XC is more than XL. Again, concept of impedance, if you come to here, resistor, capacitor, and inductor here, if you the adding the V square, total voltage V square equal to VR square plus VL minus VC square. VR square, because if you take this triangle, right angle triangle, VR square plus Vx minus VL whole square, that is equal to total this voltage V square. Again, you substitute VR equal to, or total V equal to I into Z. Z is called the total impedance of the circuit. Therefore, I into Z whole square equal to I into R whole square plus I into XL minus XC, or I cos I squared into XL minus XC whole square. Cancelling the current, we'll be getting it is equal to Z square equal to R square plus XL minus XC whole square. Or the impedance of this RLC circuit equal to square root of R square plus XL minus XC whole square. That is the, where XL equal to omega L, which is equal to 2 pi FL, inductive reactance, and XC equal to omega C, which XC equal to 1 by omega C, which is called the capacitive reactance, or 1 by 2 pi FC. Therefore, that equation is root of R square plus XL minus XC whole square equals impedance. And power factor cos phi is equal to, if you're looking into that one, this angle, power factor is given by, which is equal to R by Z. Therefore, this is another impedance triangle. This is the resistance, and this is the difference in reactance, XL minus XC, and this is the impedance, and this angle is, we call it as power factor angle, same as this one, power factor angle, which can be written as cos phi equal to R by Z, cos phi equal to R by Z. Another way of representing this one equal to tan phi equal to XL minus XC divided by R. By using both equations, you can find out what the power factor angle. Therefore, this is the phasor diagram when XL is less than XC, and this is the phasor diagram corresponding to when XL is more than XC. When XL is more than XC, net power factor, of course, that is equal to lagging. When XC is more than XL, the power factor is leading. Continuing the RLC circuit here, RLC, and in rectangular coordinate, this can be represented as Z equal to R plus JXL minus JXC. Or Z equal to R plus J into XL minus XC. Or in polar coordinate, it can be represented as Z equal to modulus of Z angle phi, where Z equal to root of R square plus XL minus XC whole square is the magnitude of this complex quantity, and angle phi equal to tan inverse XL minus XC divided by R. That's in polar coordinate. Impedance can be represented like this one. In of course rectangular coordinate, it can be represented as R plus J XL minus XC. And the power factor, as already we said, tau phi equal to R by Z, or tan phi equal to XL minus XC divided by R, or this is the impedance triangle which already we have seen, which is equal to Z square equal to R square plus XL minus XC whole square. This you can apply the, of course, a rectangular, say, Pythagoras theorem here, R square plus XL minus XC whole square equal to Z square. Now, concept of impedance, you can again see V equal to Vm sin omega t, I equal to Im sin omega t, plus phi or minus phi, that depends upon the magnitude of inductor and capacitance. Plus sign happens when omega XC is greater than XL, that plus comes, and negative sign comes when XL is more than XC, that varies. For the power factor equal to R by Z, and tan phi equal to XL minus XC divided by R, where Im, the maximum value of the current, is given by Vm divided by whatever the impedance set, which is equal to square root of R square plus XL minus XC whole square. Of course, unit equal to ohms, and this ratio Vm divided by this impedance, that is equal to the maximum value of the current Im. Therefore, I equal to Im, whatever this Vm by Z, into sine omega t plus or minus phi. If XC is more than XL, positive sign. If XL is more than XC, it is equal to negative sign. Therefore, this is again impedance triangle. Now let us see a few problems on that. A problem on RL circuit. A resistor of 50 ohms and an inductor of 0.2 Henry are connected in series across 230 volt 50 hertz supply. Find out the impedance, power factor, current, active power and reactive power. This circuit is as. Therefore, here the resistance equal to 50 ohms, L equal to 0.2 Henries, and voltage is equal to 230 volt. It's given. Frequency also 50 hertz. Then you can calculate what is inductive reactance XL, which is equal to 2 pi into F into L, 2 pi FL, which is equal to 62.8 ohms. Now in rectangular coordinates, as we have seen that impedance is equal to 50 plus 50 is the resistance, or 50 plus J 62.8, that much ohms. This is the impedance 50 plus j 62.8. In that one, the magnitude of that one is given by square root of 50 square plus 62.8 square, which is 80.27 ohms. Therefore, this is the impedance, and of course, the magnitude of the voltage equal to 230 volt. And then you can calculate what is the current. 230 divided by the impedance 80.27, which is equal to 2.87 amperes. Therefore, this is the current. Of course, to find out the power factor is given by R by Z. R equal to 50 ohms and Z equal to 80.27 ohms. Then you can get 0.62. Of course, this is a lagging. Say RL circuit, the power factor is lagging, 0.62 lagging. And phi you can calculate this is 51.68 degree. Therefore, this angle equal to 51.68 degree. Of course, the current is lagging the voltage by 51.68 degrees. Therefore, the current can be calculated. Of course, active power is equal to, as you know that, it is equal to V into I into cos phi. It's active power or true power or real power. The product of voltage into the current into the power factor, Vi into cos phi. That is equal to 230 into 2.87 into the power factor is calculated as 0.62 or 409.26 watts. And the reactive power is equal to Q equal to Vi into sin phi, which is equal to 230 into 2.87 into sine of this angle, which will be getting, it is equal to minus 514.87. This is the, reactive power, and this is the real power. Now coming to another problem, say again, it's an RL circuit. It is an RL circuit in which RL circuit, the power it is given as 160 watts. The serial RL circuit takes a power of real power or active power 160 watts, active power 0.8 lagging. RL circuit is a 0.8 lagging. Power factor, this power factor 0.8 lagging from 230 volt 50 hertz supply. Determine the value of the resistance and capacitance. For us to find out what is R and L, power is consumed equal to 160 watt and power factor equal to 0.8 lagging. These are the, of course, voltage equal to 230 volt, frequency equal to 50 hertz. The real power, as you know, the equation V I into cos phi, that is given as 160 watt and V equal to 230 watt. Power factor equal to 0.8. From this equation, you can calculate what is the current. Therefore, the current equal to the real power, active power P divided by voltage into the power factor. We'll be getting 0.87 amperes. The current equal to 0.87 amperes. That's the first thing. Once you get the current, and once you know the voltage, then you can calculate what is the impedance. Impedance means total resistance to AC resistance. You can say the AC resistance. You can get AC resistance, total resistance. That is equal to this voltage divided by the current. V by I. 230 divided by this 0.87. That will be the impedance, which is equal to 264.37 ohms. That's the impedance. Therefore, once you know the impedance, then of course, the power factor is also given. Power factor equal to 0.8 lagging. Power factor definition, as you know that one, power factor equal to cos phi equal to R by Z. Z already calculated. Power factor is given 0.8. From this equation, you can calculate what is the resistance. Cos phi equal to R by Z or R equal to Z cos phi. Z is calculated into cos phi 0.8, 211.211 or 2011.5 ohms. That is the resistance. Next one, you can have to calculate what is the inductance. In order to calculate the inductance, you have to calculate what is XL. Inductive reactance, you have to calculate. XL is given by, as you know that one, XL equal to square root of Z square minus R square. This triangle, right angle triangle, if you take XL square equal to Z square minus R square, or square XL equal to square root of Z square minus R square. From this one, you can get Z square minus R square, which is equal to 158.61 ohms. Therefore, XL equal to root of 264.37 square minus 211.5 square, 158.61 ohms. That is XL. Once you get XL, XL is nothing but omega L. Omega equal to 2 pi F. Therefore, 2 pi FL equal to XL. Or from that one, L equal to XL divided by 2 pi F. F equal to 50 to 50 hertz. Therefore, from this equation, we can XL divided by 2 pi FL. 2 pi F. You'll be getting 158.61 divided by 2 into pi into 50, which is equal to 0.5 Henry. Therefore, the answer is that the resistance value that is equal to 211.5 ohms and the inductance value equal to 0.5 Henry. Let us see another problem in an RC circuit, a series RC circuit with 50 ohm resistance and 100 microfarad it is there here. Capacitor equal to 100 microfarad and it's connected to a 230 volt 50 hertz supply. Calculate the impedance, current, power factor, voltage across the resistor and voltage across capacitor. R is given 50 ohms, C equal to 100 microfarad, voltage equal to 230 volt, frequency is given 50 hertz. Then you have to calculate what is the capacitive reactance 1 by omega C, 1 by 2 pi FC, 1 by 2 pi 50 into, of course, C, 100 microfarad, we'll be getting 31.83 ohms. Similarly, you have to calculate what is the impedance. Impedance is given by square root of R square. This is the impedance equal to root of R square plus XC square. You'll be getting root of 50 square plus 31.83 or 59.3 ohms. And power factor is given by cos phi equal to R by Z. From that one, you can get power factor equal to 50 by 59.3. Of course, 0.843 leading. Since the RC circuit, power factor is leading, phi equal to 32.54 degrees. And the current can be calculated. Current equal to, of course, the voltage divided by what is the impedance, 59.3. You'll be getting 3.89 amperes. And the voltage across the resistor, equal to the current through the resistor into the resistance. For 3.89 into 50, 194.5. And voltage across the capacitor is given by current through the capacitor into the capacitive reactance XC. 3.89 into 31.83, which is equal to 123.82 volts. Now let us see one more problem, that RLC circuit. In a resistor of 50 ohms and an inductor of 0.1 Henry and a capacitor of 40 microfarad are connected in series across 230 volt 50 hertz, and find out the power consumed by and the power factor. It's a RLC circuit. Of course, R is given as 50 ohms, inductor is given as 0.1 Henry, capacitor is 40 microfarad, voltage equal to 230 volt, frequency equal to 50 hertz. These are the data given. Inductive reactance you can calculate, X equal to 2 pi FL, 2 pi into F into L, you'll be getting 31.4 ohms. And capacitive reactance is given by 1 by omega C or 1 by 2 pi FC, 1 by 2 pi into 50 into C, that is 40 micro, that is 79.6 ohms. And the impedance is given by Z equal to root of R square plus XL minus XC whole square, root of 50 square plus 31.4 minus 79.6 whole square, or 69.4 ohms. Then power factor is given by, as you know, the power factor is given by R by Z, resistance divided by the impedance. R by Z, 50 divided by whatever the impedance calculated, 69.4, or that's equal to 0.72 lagging. This is equal to 0.72 lagging, or phi equal to 43.95 degrees. And current I equal to, the magnitude of current is given by voltage divided by impedance, which is equal to 230 divided by 69.4 to 3.31 amperes. And the power consumed by the circuit is given by voltage into current into cos phi, power factor. Voltage equal to 230 volt and current equal to 3.31 amperes and power factor equal to 0.72. Therefore, the power consumed equal to VI into cos phi, 230 into 3.31 into 72, which is equal to 548.14 watts. In this problem, since we can see that XC is more than XL, therefore XC is more than XL means here previously I told it is a lagging power factor. It's not lagging power factor, it's a leading power factor. 0.72 leading, actually phi equal to this much, because you can see that capacitive reactance is more than inductive reactance. This is a triangle, impedance triangle, therefore it is leading only. It's a change, it is a leading. Power factor angle equal to of course the leading, cos phi equal to 43.95 degree angle and equal to 0.72 leading. It's not lagging.